Hi everyone, and welcome to the next lesson in Activity 17.2. We are starting today on page 248 in your Springboard book, and you're going to want a pencil and a calculator. So we've talked a lot so far about our new transformation dilations. And just like we can have a composition of transformations that are rigid motions, we also can have a composition of transformations that is going to map something onto something else, including dilations. Now, so there isn't one singular transformation that's going to make figure A onto figure B, because it's going to either need some sort of rotation or translation, and it's also going to need for sure a dilation of some sort. So one of the things that we could do is a dilation and a rotation to make figure A onto figure B. So to practice again with our composition of transformations then, we want to remember a couple things. First off, with these compositions, we start with the rightmost thing listed. So remember, little r means reflection. So what we're going to do is we are going to start by reflecting our initial 3 points, which are 2, 3, 2, 1, and 6, 3, over the line y equals 1. Okay, and then this is the line y equals 1. Now, the reason I remapped this down here is notice the scale is different from the original picture as it is down here. So here's the original picture on a different size scale. I don't know why the book decided to do that. It's kind of mean. So here's our original picture. So if we reflect this down, if we're at 2, 1 down here, excuse me, this is what it should look like. When we reflect this, what you're going to notice is 2, 1 is going to stay put. And then 2, 3 is 2 units away from our line of reflection, so it's going to map down here. And then 6, 3 is going to move down here. So here's our initially reflected points. A prime, which is at 2, 1 still. B prime, which is at 2, -1. And C prime, which is at 6, -1. Okay. Now from here, the second thing they want us to do is a dilation with a scale factor of 2. So we're going to take these new points and we are going to multiply everything by 2 to find our final location. So 4, 2, B double prime is going to be at 4, -2 when 2 and -1 are multiplied by 2, and then 12, -2. Okay, so if we graph that final piece, we would see that's probably why they changed the scale so much on us, that because this would be blown up so much to look like so. Okay, so 4, 2. So this would be our final product there. Okay, so again, first on the inside, and then the one that's leftmost will be the one you complete second. Okay. Now for part B, if we take our original points, we're starting this time with a dilation. So we're going to take our original points A, B, and C, which I have listed over here, and we're going to multiply each of those by 1/4, aka divide by 4. So 2 times 1/4 is 1/2. 1/2 times 1/4 is 1/4. And then B is going to be multiplied by 1/4, and we're going to end up with negative, oops, excuse me, not negative. My gosh, what am I doing? 2 times 1/4 is 1/2. And then 3 times 1/4 is 3/4. And then last but not least, we have 3/2, 3/4 when we multiply 6 and 3 by 1/4, our scale factor, okay? Now this next part requires us to then do a rotation 90 degrees counterclockwise, right? We'd be going 90 degrees that direction, which means what we would have to do is take our points and we are going to flip-flop X and Y, and the X value is negated. Excuse me, the Y value, the new X value, is negated. So when we put these into that function rule, we're going to see is that 1/4 and 1/2 are going to switch spots, and now 1/4 is negative for A double prime. And then for B double prime, again, we're going to flip-flop the location of 1/2 and 3/4, and then 3/4 is negated, again, going back to our function rule. And then last but not least, C double prime, you're going to flip-flop the location and negate. Okay, so there again would be our final location on these. Okay. Now, last but not least, what we're going to see here is we would have a 3-part where we're not only dilating, but then we're translating to the right 2 and down 2, and then we're dilating again. So again, we can kind of keep going with these transformations. Always start with the rightmost, and then we can keep moving on with our transformations. Okay. Now, what all this leads back to, again, then, is the idea that, again, they are similarity transformations. Because in all of these, the pre-image versus the image, they are the same shape, but a different size. Okay? That's the big thing with what we're seeing here with these dilations. So again, these are called similarity transformations because they keep that same shape, but they just change our size. So if we look at these vocab words that we have talked all about congruence transformations being our translations, rotations, and reflections. Now, those are also going to be considered similarity transformations because they don't change shape, right? They don't change size either. So the translations, the rotations, and the reflections are all considered both congruence and similarity transformations. The one that is only going to be a similarity transformation are the dilations because they change the size. Okay, so we would call all of these figures similar to each other because we can use similarity transformations to make one figure into the other, whether that just be one or a composition like we've been dealing with in these last couple problems. Okay. So again, explain why rigid motions are considered similarity transformations. Well, they are considered similarity transformations because rigid motions, which we talked a lot about earlier this year, preserve the shape, so they are similarity transformations as well. So it's a very important fact that they keep that shape the same because then it's also going to put it in the category of similarity, even though they also don't change the size, okay? All right, so thanks for watching, and we will work more with this in class.